I now call to order the Society's 2430th meeting in the 149th year since its founding on March 13, 1871. Good evening, everyone, and welcome to another installment of the Fall Lecture Series produced by PSW Science. Because of COVID-19, the Society is bringing these meetings to you via Zoom from locations all around the globe, rather than our usual home, the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. Tonight, we will hear about the German Triple Project to land a space probe on Jupiter's moon Europa, penetrate the ice crust, and launch an autonomous underwater vehicle to explore the subsurface ocean and collect and analyze data samples to look for signs of life. Our speaker is Triple's co-director, Christoph Waldmann. I'm Larry Milstein, President and Program Chair of PSW Science, one of the oldest scientific societies in Washington, D.C. PSW Science is a 501c3, non-profit education and science organization whose mission is to provide a forum to exchange scientific ideas, further scientific understanding, and encourage scientific inquiry. This lecture is being recorded and will be posted to the PSW Science YouTube channel, where it will join over 145 other recordings of PSW Science lectures. We invite everyone to take a look and explore these presentations. And if you like what the Society is doing, we invite you to become a member through the PSW Science website, www.pswscience.org. Membership is a foundation of the Society. I encourage everyone with an interest in science to join. The Society is grateful for the sponsorship of the 2020-2021 lecture series by the Policy Studies Organization in cooperation with the American Public University and a generous donor who is asked to remain anonymous. We thank all of our sponsors. Before we turn to the lecture, it is the tradition of the Society to welcome new members and read the minutes of the previous meeting and the summary of the previous meeting's lecture. I am pleased to announce that the following new members have been elected to the Society. Andrew Bomey, a senior advisor at Davis Capital, interested in projective geometry and cosmology, who learned of the Society from PSW videos on the internet. And tonight's speaker, Christoph Waldmann, who learned of PSW through our invitation to have him give tonight's lecture, and whose interests will be clear in part from his lecture tonight. We welcome them both to membership. Recording Secretary James Heelan will now read the minutes of the 2429th meeting and the lecture by Rob Bertram. His lecture, Golden Rice, is available to everyone without charge on the PSW Science YouTube channel, the PSW Science Vimeo channel, and it can be accessed directly from the PSW Science website, www.psscience.org. James, it's over to you.
Thank you, Larry. On November 20th, 2020, by Zoom video conference broadcast on the PSW Science YouTube channel, President Larry Milstein called the 2429th meeting of the Society to order at 8:03 p.m. Eastern Standard Time. He announced the order of business and welcomed new members. The recording secretary then read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, Rob Bertram, Chief Scientist in the Bureau for Resilience and Food Security at the U.S. Agency for International Development. His lecture was titled Golden Rice, an adventure in science to improve nutrition. Nutrition is a unique global challenge. In 2007 and 2008, global prices of staple grains skyrocketed, adversely impacting the food security of people around the world. In response, the United States and other G7 member countries launched the Feed the Future initiative. Stunted child growth is the standard marker for chronic malnutrition. It reaches 40 to 50% in some agricultural zones. Feed the Future's objectives include reducing child stunting within those zones by 20%. While the Feed the Future's objective is global, diverse nutritional status demands diverse solutions. For example, energy deficits and micronutrient deficiencies remain high in low-income countries because people do not eat enough animal-based foods, fruits, and vegetables. But in high-income countries, hunger and child stunting are comparatively low, and obesity is the principal nutritional challenge. Bertram said diet is the best means for addressing nutritional deficiencies. He acknowledged movements away from animal-sourced foods in high-income countries and advocacy for certain diets, such as Eat Lancet, that purport to strike the ideal balance between climate impact and human health. But, he said, those diets are cold comfort for populations who cannot afford them. Biofortification is an approach to mitigating micronutrient deficiencies by building nutrition into crops that, after an upfront investment, is affordable and sustainable. Golden rice is an example of biofortification. Populations with rice-centric diets experience higher rates of certain micronutrient deficiencies. Rice is an available, affordable, and satiating food, but it is deficient in micronutrients, including vitamin A, iron, and zinc. Vitamin A deficiency causes blindness, increases the mortality rate of children, and increases the fatality rate for certain diseases. In the Philippines, vitamin A deficiency remains high in its rural and poor populations. In Bangladesh, the deficiency exists population-wide. Bertram said rice lacks the genetic variability to breed a strain that would provide vitamin A. To solve the nutrient deficiency, a partnership including Filipino and Bangladeshi scientists employed a biotechnological approach to produce golden rice. This rice, which is golden color, bridges the gap in the carotenoid biosynthetic pathway by introducing two new genes, a phyotene synthase from maize and a carotenoid desaturase, CRTI, from a common bacterium. These genes lead to the equal production of beta-carotene and lycopene in the rice. Bertram said a 100-gram portion of golden rice could supply 30 to 40% of the recommended daily intake of vitamin A for children. The chemical difference between golden and non-golden rice is exactly the same, according to Bertram, except for the beta-carotene content. Because yield performance is also comparable, Bertram doubts golden rice will demand a premium price. The Philippines and Bangladesh are currently reviewing golden rice for commercial propagation. Food regulators in Australia, Canada, the Philippines, the United States, and New Zealand have already approved golden rice for consumption. Bertram said biofortified foods are more likely to gain popular acceptance than other means of addressing micronutrient deficiencies. Accepting golden rice, biofortified foods usually look the same and taste as good or better than the products they seek to replace. Biofortified foods are also generally available to all members of a household, and they are sustainable and affordable after upfront investment. Because nutrition impacts long-term health and productivity, Bertram said it should be seen as an economic issue in addition to a health issue. By considering economic impact, Bertram said the value in developing biofortified foods is indisputable. Scientists are currently making progress in biofortifying crops through breeding, such as pearl millet and beans to produce iron, wheat, rice, and maize to produce zinc, and sweet potatoes, cassava, and maize to produce vitamin A. Biofortified crops are steadily increasing in acceptance from 1.7 million smallholder farm households growing them in 2014 to 8.5 million in 2019, reaching almost 50 million people. Rice remains a challenge because it cannot be bred to increase iron and vitamin A content. Bertram said that the objective may only be achieved through genetic engineering. He then responded to arguments against genetically engineered crops, including with examples of demonstrated pest-resistant, food-safe crops and Green Revolution wheat seeds that have been widely grown for almost 50 years. The speaker then answered questions from the online viewing audience. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 10:06 p.m., President Milstein adjourned the meeting. Temperature on Washington, D.C., 11 degrees Celsius. Weather, clear. Concurrent viewers of the Zoom and YouTube live stream, 54, and views on the PSW Science YouTube and Vimeo channels, 177. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. The minutes will be posted to the website in due course. Please send corrections or comments on the minutes to corresponding secretary Robin Taylor at correspondingsec@pswscience.org. We now turn to tonight's lecture, the Triple Project, to explore Jupiter's icy moon Europa. And it is my pleasure to introduce tonight's speaker, Christoph Waldmann, who is joining us in the wee hours of the morning from Germany. Christoph is an ocean scientist, a research manager for European and German national funded projects, and an expert in spatial data infrastructures. He is the co-director of the Triple Project, and he leads a research group at the Center for Marine Environmental Sciences, a research faculty at the University of Bremen, funded through the Excellence Initiative of the federal German government. He also serves as a member of an expert team of the World Meteorological Organization and as a lecturer at the Technical University of Lübeck in Germany. His academic research is focused on the development, application, and evaluation of ocean sensors and underwater platforms, and on bridging the gap between ocean and space sciences to promote the exploration of ocean worlds. He is an author on more than 100 technical papers and book contributions, and he has given many presentations on ocean sciences, data management strategies, and emerging technologies in oceanography. He is a senior member of the IEEE Ocean Engineering Society and a member of the American Geophysical Society. Christoph earned his diploma degree and his doctorate in applied physics at the University of Kiel in Germany. All questions will be fielded after the lecture during the question and answer session. Christoph, the screen is yours.
So, hello everyone and good evening from Germany, and those of you who are living in my time zone, good morning. So it's a big pleasure for me to have the opportunity to give this webinar, and I hope it will be of interest for you. As Larry mentioned, I'm not a real expert in space science, but I've been working in the field of ocean science for over 30 years now. But during the past couple of years, I had been in touch with space sciences, and it was very inspiring for me. And so maybe I can also convey this enthusiasm that I developed for space sciences as part of my presentation. Okay, so I start here with the first slide. So what can you expect from this webinar? What I wanted to show you is the reason why Europa is of high scientific interest. And I also would like to give you an overview of what is known about Europa up to now. Then an overview of a mission scenario to explore Europa. Europa will be shown, and then we go more into the details of the Triple Project, which mainly deals with technical concept for an under ice mission to explore the ocean that is supposed or that's existing below an ice sheet on Europa. And at the end, I would like to raise up a few questions, and maybe we can start a discussion on some fundamental considerations. Okay, as a first start, for this presentation, I would show this animation that has been produced by NASA. And what you see here is actually a picture of Europa. You see the structure, the morphology of the planet with all these dark stripes, which appears to be fracture zones. And Europa, as been mentioned, is a moon that belongs to Jupiter, our largest planet. And what you see here now is a cross-section through Europa, which actually shows the upper part with the icy layer of about 10 kilometers thickness and the ocean that has a depth of about 100 kilometers. So these details I'll get back to later on. And so this is something that we have to consider as soon as we start designing an experiment or an exploration mission for that Europa ocean. Okay, so first of all, I start with the overview of the Triple project. The Triple is actually an acronym, and behind this acronym is the terms Technology for Rapid Penetration and Subglacial Lake Exploration. It's a 5-year project funded by the German Aerospace Agency, DLR, and this department is called Space Science Management. The program manager is Oliver Funke, and I think he is also listening to this presentation right now. And he actually was the one who was supposed to give this presentation, but due to other obligation, I had to step in for him. Okay. Okay, here are the triple mission goals that I would like to show. And as I mentioned, we want to develop and build a dedicated tool set to explore oceans and lakes on planets and moons of our solar systems with a focus on Europa. And you might know that these planets and moons are called ocean worlds or sometimes icy moons. It's not just Europa, there's Enceladus and Titan where similar oceans have been detected. And so that's also something that's under investigation to what degree this can be explored. So this tool set is primarily focused or built for Europa, but what we would imagine is that some of these ideas and concepts could be used for other missions as well. Think about Mars, where also water has been found. And in case that there are deeper lakes, more than just a few meters, it might make sense also to think about an exploration of the liquid water on Mars with such a system that we are planning to build. Okay, so what we want to build, we want to also validate and demonstrate that we achieved the goals and that it's actually ready for space exploration. And the way how we want to do that is we want to make demonstration missions in Antarctica. And you might know of Neumann Station. Sorry, I think I have to use the spotlight again. Yes. So what you, oops. Oh, sorry, that was my confusion here. I have to go back. I wanted to use the pointer so you can see what I'm talking about here. So what you see here is the Neumann Station, this third version. And this is located in this area. What you see here is the southern part of South America. And so that's at the ice edge. That would be one of the areas that we would use for our demonstration missions. And the good thing about this is we have infrastructure that can be offered. And in case something goes wrong, we can easily fix everything inside the station. So that is an ideal infrastructure to carry out our test. But the final aim is to go to Dome C subglacial lake. And the reason why we plan for that is we have to penetrate a rather big ice sheet of a dimension of 4 kilometers. And below that, we have a lake that is several hundred meters deep. So that comes very close of what we would expect for Europa. So very similar scenario. Okay, these are the partners. Actually, we have 8 partners involved from all over Germany. It's actually 4 locations. And with these institutions, these partner institutions, there are 26 research groups who will work on this project. Here comes the timeline. I mentioned this just started the project. Actually, start date was September 1st, 2020. And so what we have here now is a first concept phase that will end in August 2022. And from there on, we will move over to a realization phase and finally a demonstration. So we assume that in 2024, we are ready to carry out a demonstration at Neumeier and hopefully also at Dome C. So that would be the 5-year period that we are covering. And I mentioned before, the long-term goal is to go into space. This will be then a continuation of these activities, hopefully also with other partners from Europe and North America or Japan. So that's something that we have on our agenda. So it's important to build up links to other institutions in the world who are also interested in this topic, and there are quite a number of those. And I just pick out 2 networks or institutions in the US that have direct interest and that we are in touch with. And there's one project, it's called NOW, Network for Ocean Worlds, that also started this year. This is led by someone from the oceanographic field, Chris German, who is working for Woodsole Oceanographic Institution, which is located in Massachusetts. So it's a real networking activity. It shall bring PIs together who have interest in this topic and who are mainly working on earth sciences. And the idea is to do comparative studies to see what processes you see on Earth in regard to geophysical processes or processes in the ocean or anything that's related to biology, and then try to figure out how this can be transferred to planetary science. So in the way how this operated is they organize workshops, and these workshops then are used as a base to develop concept for future missions. So the other activity that's going on is NASA. NASA is very strongly involved in all activities that's related to Europa exploration. And what you see here is a picture of a lander mission that has been conceived and shall be carried out in the near future. The person who is actually leading all these activities is Kevin P. Hand from NASA, working for Jet Propulsion Laboratory. And this is a very active initiative currently. That's not clear when it can be actually implemented. But in any case, this is also a partner that we are working very closely together. Actually, there are projects already running in the Arctic where JPL is involved, and our partner of Triple Alfred Wegener Institute as well. So there are already strong links between these activities, and we will build up on that as part of Triple. So to go a little bit back into history, how it all evolved, I think 30 years ago, no one has really expected that we can find oceans on other planets or moons. And so the first mission that actually brought insight into that was the Galileo spacecraft mission, which primarily was meant to go to Jupiter and then visit the moons of Jupiter. And one of these moons is Europa. And you see here the timeline started in 1990, and then the closest flyby of this icy moon Europa was 1997. This is, by the way, the typical flight time from Earth to Europa. This round about 7 years that you have to take into account or have to expect. So the key findings of Galileo mission was that the existence of a liquid water ocean has been derived from magnetic field measurements. And there had been also, from the pictures that had been collected, the volcanic ice flows discovered. And so an idea of melting, rafting of ice could also be derived from these pictures. And furthermore, there was hint of existence of a tenuous atmosphere on Europa. So that was, so to say, the revolutionary part. You think about liquid water ocean on Europa. This is something that probably many people haven't expected in the past. So, and that was very inspiring for a lot of people. And actually, I can remember first discussions going on where colleagues from DLR were also involved. That was 16 years ago. And since then, actually, I always have an eye on these developments going on there. So the next major step was the Cassini-Huygens mission to Enceladus and to Saturn. And this has been launched in 1997. And so Enceladus had been closely investigated in 2005. And at that time, the first indications that there also is an ocean that covers the surface of Enceladus was detected. And it's the same structure as with Europa. You have a very thick ice cover, and below that, there's a liquid ocean. And yeah, what was also quite spectacular, that plumes were detected, which means that water was spilled out from the ocean through cracks in the ice sheet. And actually, these plumes had been detected by chance. It was just the sunlight was in a very advantageous direction and suddenly showing these very tiny little bubbles that are part of forming these plumes. And the opportunity has been used to investigate the plumes, and then one also found some indication of hydrothermal activities. And this is something really spectacular to think about that. That also gives an indication that this is something that should be invested more closely. So at that time, the mass spectrometer that has been on board was not able to detect molecules with higher mass numbers, and therefore it just stayed at that point. So, and I'm pretty sure there will be follow-up missions to investigate these plumes in more detail. Okay, so now I'm looking a little bit into the future. So this knowledge was very inspiring and people were getting very enthusiastic. And so there was mission plans developed also by NASA and ESA. And the NASA mission was a Clipper mission that is now has been advanced quite a bit. Actually, I think the plan was to start the mission in 2022, something this range. And this could be a very important step towards a landing mission for Europa. And to be able to collect the information that will be relevant for such type of landing mission, the Europa instrumentation was designed to provide adequate information, which, for instance, is a camera system to map the moon's surface at higher resolution than we have today. And also, it's very interesting to seek for evidence of geologic activities. These are the spots on the Europa moon that could be of high interest for further sampling and investigations. Ice penetrating radar. This is the idea to have a more detailed view on how deep the ocean actually is, whether there are shallow regions, whether the oceans actually cover the entire planet, or whether there's this rocky solid core actually also goes up to the ice surface. So it's the exact structure is pretty much unknown, and this ice penetrating radar will help in getting more details on that. And magnetometer will also help in this process. Surface temperature measurements is something that could give an indication of plume activities, or to say it more precisely, on some volcanic activities, maybe hydrothermalism, or whatever the reason may be. So this is an important parameter to look at. And the spraying from the ocean to space as plumes is something that also will be carried out with other instruments. I didn't want to go into all the details. So from this, you can derive a long-term plan. And as I said, Europa Clipper is almost ready to be launched. It has been advanced quite a bit. And if you think of time frames of 2 or 3 years, can expect that many components are already advanced at a major level. And so that's would be a very important step to prepare a lander mission. And at the moment, JPL, Kevin Hand, I mentioned his name before, is very active of designing a Europa lander concept. So this will not go through the ice, but just stay on the surface and then excavating material from under the ice down to a few centimeters. So the issue is, for the moment, it's not known whether there are actually flat surfaces, and that's something that the Clipper mission shall provide as an input for the lander concept. So you see there's a strong linkage between these two missions. And what I want to say is here, what we would see as our contribution would be the ocean exploration part. And with our triple project, we hope that we can get NASA interested, and that they would more closely look into what is good and what might be useful for this type of mission. And we are hoping that we can have some success and then finally find some way of cooperation. Okay, ESA is also busy in this regard. This ESA Juice mission had been a planning phase of at least 10 years. And as you see, there's still the idea that it will be launched soon in 2022. Not sure whether this schedule will hold. In any case, they have advanced quite a bit. And same as with the Clipper mission, it will not be a landing mission, it will be orbiting mission. And the idea would be the same or similar idea as with the Clipper mission, to make a detailed survey of Europa moon's surface structure, plumes, and morphology. Here are the instruments that will go on this mission, and you see there's some overlap between what Juice is planning and Clipper. There are some differences if you look at the ice penetrating radar in regard to the resolution and the penetration depth. And so from that perspective, you can see them as complementary. Okay, and I'm not sure, I think this hyperspectral imaging spectrometer is unique to JUICE as far as I know. Okay, so this is the, so to say, preparatory work, but as Larry already mentioned, there's this idea to look for signs of life, and this is here the timeline of life on Earth, and you probably all have looked at it several times. And I just wanted to emphasize here a certain period of time that goes back to 3.8 billion years to 4 billion years. And that seems to be the time frame when the oceans on Earth has developed, and associated with that, the earliest life form had been also dated back to this time. So there's this close relationship between the occurrence of oceans, lakes, or water as such, and the occurrence of life forms. And it's very difficult to look further back, but some people say more or less life has existed on Earth even from the beginning. But this is very difficult to detect or to find out. But you know, this connection between life and water is crucial, and that's also the reason why people would like to explore Europa in more detail. And this is one of the most striking facts. Okay, I come back to this, what is mentioned here on the right-hand side later on. However, thinking about detecting life forms on Europa, it can be difficult. You know, if we see, for instance, in the oceans, big fish or any life form that obviously, so to say, can be recognized as living matter, this is then the easy part. But what people would expect is that this will not be the case. So typically, one would look for bacteria or any sort of microbial life forms. And this is now getting very difficult. You know, you can look at the structure, say, okay, this is very interesting, but it could be also accumulation of organic material. How can you actually determine whether it's a life form or something that has been clustered just randomly? So this is a big issue, you know, and this is, by the way, has been also formalized. There's a so-called ladder of life that has been developed by NASA, and this is a very interesting concept to help in this process. But you should keep in mind, there's actually no actionable definition of what the life actually means. How can you characterize it? This is very difficult. And because of that, people are getting a little bit more careful. Instead of saying we are looking for signs of life, sometimes they just talk about biosignatures. And this actually means they're looking for extant life form. Okay, this is a NASA vision for a lander mission to Europa, and you see what I just mentioned here again listed. There are actually 3 science goals. As I mentioned before, biosignature has a very high importance, very high priority. The habitability is connected to the existence of water. And sure enough, there are other parameters that will be considered as well. And the surface properties, so the geophysical structure is also of high importance to judge where to look, where the best place is to take samples. So why is Europa in the focus? So I mentioned before, and you probably know, there are other moons in our solar system that could be of high interest to look for life forms or for biosignatures, or for extinct life forms. So what we assume, or what is assumed on Europa, is that energy sources exist. And one of the energy sources are the tidal currents that are produced by the gravity of Jupiter. It seems that there are some biological essential elements what can be expected. We have liquid water, and finally there's a very important topic, a very important point to mention. It's assumed that this ocean on Europa has been in existence for the past 4 billion years. So very similar to the oceans on our home planet Earth. This cannot be said about other oceans like Enceladus. So there are ideas or some concepts and models that the ocean had been completely frozen during certain times, which is connected to the orbit that this Enceladus is moving along around Saturn. So very important. This is the reason why Europa is in the focus, because we're assuming that there was enough time that life form could have developed. So what is known, I already mentioned a few of these things, so I can probably go through this quickly. Ice thickness, probably tens of kilometers. Maybe there are regions where it's just a few kilometers thick. This is actually a big technical challenge. And another thing is tidal currents. I mentioned it. There are strong tides that we can expect, but due to the high depth of the oceans, this probably the tidal currents are not as strong as on Earth. And just to give you an idea about the water volume, what is assumed is that Europa harbors about twice as much water compared to Earth. That's again related to the big depth. Also, maybe you have seen this before. If we talk about the ocean depth of 100 kilometers, the pressure in 100 kilometers depth is about the pressure in the deepest point in the world ocean. So it's about 1100 bars. So it has to do with the different gravity. So I would like to come back to the topography, and what you see here on the left-hand side is the picture that shows the morphology of Europa taken by Galileo mission. If you look at similar pictures from Earth, you see here on the top right panel, the Mount Everest region, and on the lower part, the Death Valley with Devil's Golf Course. So both, in all cases, we have a resolution of 10 kilometers. And so it's very difficult to judge from there how deep the trenches are and how the actual morphology looks like. It's almost impossible. So that's a very important part of the Clipper and Juice mission to find out what the exact morphology will look like. So it's still pretty much unknown. Also want to mention that the radiation is very high. It's 18 times as much as on Mars. It's also causing a lot of technical issues. Surface temperature is pretty low, and ocean water temperature, because of the pressure, can be something like minus 13 degrees centigrade. That's how the mission could look like. First, a landing phase, melting through the ice, and during this phase, samples can be taken and measurements can be taken. And finally, there's an underwater vehicle deployed in the ocean. That's where, so to say, triple will kick in. So what we are planning to do is exactly this. We will look more closely into how we can accomplish these 3 steps. So while we are not talking about a landing system, but what we want to do is to put an astrobiolab on the surface of the ice shield. Then we will have a melting probe, and then you see again this underwater vehicle that shall be deployed in the ocean. Okay, here comes a few animations. So this is more like what we have to think about. We can probably just build a very tiny little system that goes through the ice. Typically, the diameter of these melted holes are 10 centimeters. So we have to think about very tiny little AUV system, which is actually a disadvantage. Usually you would go the other direction. You want to build big underwater vehicles. Has to do with the hydrodynamics and energy supply and so on. So that's a big issue, and we have to make sure that a proper communication will take place between the underwater vehicle and the rest of the system. And sure enough, there has to be enough autonomy included in the vehicle, because typically we will lose control. We cannot directly steer the underwater vehicle. It has to carry out its mission on its own. Here again is a scheme that shows what we have in mind. And so what is added to this scheme is that we think about taking samples with the melting probe and also with the nano AV. And these samples should be brought back to the surface. So our melting probe shall go in both directions. So it melts down and should melt up. Yeah, there is a lot of investigations going on also from JPL's side, and there's University of Washington. People are working on this in quite a bit of detail, and a number of experiments had been carried out. As far as I know, the maximum depth that had been reached were 400 meters. So we are still, there's still a gap to reaching these 10 kilometers that's necessary. And so typical speed that you can go through the ice is 2 to 6 meters per hour. Okay, I will show this later on the slide, what this means to go through 10 kilometers of ice. And you also have to take into account that it's not just ice. You can also have sediment in the ice, so you have to include water jets. So there are some technical issues that have to be kept in mind. This graph shows now what it means to go through 10 kilometers of ice. This is here the ice thickness on the y-axis, and on the x-axis is the time that you need to melt through the ice. And it's something in between, say, if 200 days to 600 days. So let's say something like a few months up to 2 years that you have to consider will take to go through the ice. So this is definitely a major challenge that we have to face. And you know, there is always an issue that some technical failure will occur, and then the whole mission is at risk. So there's a lot of work and thought that still has been spent on that. The other thing that you probably have been thinking about as well is you need a lot of energy. And so you can make a quick calculation, and then you will find out to go through 10 kilometers of ice, you need something like 10 megawatt hours. That's a lot of energy. And so do this with batteries is probably not possible. And therefore people are thinking about using the so-called RTGs. This is something that has been used before in the Cassini-Huygens mission, as you might know. And that was also a reason why the operation could be prolonged for such a long time. Actually, the mission had taken measurements and pictures for several years, and therefore these RTGs were crucial to allow for such type of mission. Okay, this will be the case for Europa as well. and people are getting serious on that. And besides that, you have to think about that you are very limited in space. Still, you have to ensure that there's enough battery power available for the electronics or for the analytic system. And for the nano AUV, it will be quite moderate. We're just thinking of, in the small size AUV that we have in mind, this underwater vehicle, just 500 watt hours, which probably will be good for operation time from 2 to 3 hours. And so if we want to prolong this, we have to recharge this by docking. Okay, so here another idea. So this there's still the issue of how can we have control over the system. So we have to ensure that there's some communication set up. And the way how it's done is that that the melting probe is combined with systems that could allow for this transmission. It's actually relay stations that could be deployed in the ice, which are called PAC. And actually to go through the ice, we can use electromagnetic waves. This does not work in water, but in ice it's working. And so these PACs could be relay stations that are operated with RF communication system. Here's just an overview on how this could look like. You have an orbiter that is used in around Jupiter to allow for communication with Earth. Then you have the lander with an RF transmitter, and then you have these relay stations, PACs in the ice that could set up the communication link to the melting probe and finally also to the underwater vehicle. So also a big topic. That's something you cannot expect that you have a real-time control of the underwater vehicle, but at least that you check the health status and maybe even retrieve some of the science data by using that. Here comes another issue that you have with communication. It's related to the fact that Jupiter is pretty far away and you have to expect delay times of 33 to 53 minutes. So that's another argument to have enough autonomy included in the AUV to allow for a mission carried out without interference from outside. So no human in the loop in that case. So that's one of the reasons why the autonomous operation is a major priority of all in the planning phase also of Triple. So if you look into what it actually means to go with underwater vehicle under the ice, you have to be aware that there's a major issue related to how this vehicle can orient itself under the ice. So navigation, positioning is a big issue. It's completely dark. Camera systems are not easy to use. Maximum distance maximum range that you can see is maybe 10 meters. So you completely rely on sonar systems. And sonar systems have their particular issues. Okay, this is an example shown here with the seabed AOV of Woods Hole, who's had done a mission under Antarctic ice. And so it's always a big risk. This is not a routine mission that's carried out, but something that has still this exploratory character, and reliability is still an issue. So people are very careful in designing these type of experiments. The other thing is that you can have pretty strong currents under the ice, which is related to the morphology. And that's something that we probably will experience in Antarctica as well, also close to Neumayer Station. Neumayer Station is on shelf ice, and below the ice you have the ocean, and there are currents which can actually go up to 1 knot. This is actually the current that you can expect below the ice of the Neumayer Station. And this is the good thing is you can predict them very well, so you know when to deploy. the system to be sure that it will come back, and that in case it cannot fight these currents, you have to these high currents of 1 knot, you have to look for times where the currents are lower. It's a big issue for Europa, by the way. Okay, now here comes our design ideas of the nano AOV. And so basically the principles that we have in mind is highly efficient propulsion. And what you see here is a streamlined shape with wings. And this is something that is used in ocean sciences today, not in this size, but size of, say, 40 centimeters length and 10 centimeters in diameter, but it's in a bigger size, so-called underwater gliders. And this have proven to be very highly efficient. So if we think of Europa, we have to keep in mind that we have to reach depth of 12,000 meters. This is probably something that we cannot achieve as part of triple, but what we are doing is we're looking for maximum deployment depth of our system that has to be designed of 4,000 meters. The speed, as I mentioned before, is related to the currents that we expect. So 1 meters per second is something that we will aim for. And the overall weight should be kept low because everything has to be compensated. Underwater vehicles are typically neutral weight underwater. So everything has to be compensated by buoyancy material. So we were playing around with different ideas. And by the way, here you see the dimensions that we have in mind. And you also see here the range that we are planning for, 8 kilometers, that goes along with this 2 to 3 hours endurance that I mentioned before. And what we would like to explore a little bit more detail is a jet propulsion system. So not just 1, but 4, that would also allow us to have a steering capability of our system. Whether we will use wings or not is still not clear. But in any case, I think it's not enough just to use a glider principle. We also have to add a propulsion system to carry out the docking that we actually need to do repeated missions under the ice. Here are some examples of sensor systems that we have in mind. There's a very interesting development that has been carried out in Switzerland, which may be useful for biosignatures. This is a chemotaxis assay to capture bacteria. They're actually lured into these troughs and then, so to say, sealed and will be investigated. Other sensor systems like salinity and temperature that are used for habitability are already there. And the size of the sensors is not a big issue. Typically, the size of underwater vehicles are determined by the sensors. This time we do it the other way around. We fix the size and then look for the right sensor systems. It's pretty unusual, but it's the way how we operate. So finally, I would like to say a few words about the issue of underwater sound propagation, because it's so crucial to position our vehicle and to get information. You know, everything is dark. If we have not enough light on board of our vehicle, we have to rely on sonar system. And the issue is that the sound channel is quite difficult. So that has to do with the fact that we have a lot of reflections. And you see here an example. It's not just the direct ray going from the transmitter to a receiver that contributes to the signal here, but we also have this multipath, which leads to a pretty difficult structure of the signal. And another issue of the underwater sound channel is the Doppler effect. And this is always underestimated. It's significantly higher than compared in air. Many people say we have such a good solution with cell phones. Can we simply transfer this concept to underwater? No, it's not possible. And one of the reasons is pretty strong Doppler effect. Good. There are some ways how to deal with that, in particular if we think about communication, and some bio-inspired approach can help us here. And so dolphins have a special way how to communicate between each other, and they are using sort of frequency sweeping is a technical term that is used here. You see here the frequency on the y-axis and the time on the x-axis, which means it's a spectrogram. And you see here there are changes in the frequency why this communication is, so to say, carried out. So this is a good way to avoid the issues or circumvent the issues that you have because of the underwater channel. And here comes now the underwater navigation system, which typically relies on transponders. And sometimes you are just rely on dead reckoning, meaning that you scanning the sea floor or the bottom of the ice edge, and then like you know it from computer mouse, detect the position where you are. The issue is the accuracy is not very high and updates rates is also pretty low. So this is completely different to terrestrial application, and this causes a lot of headaches to deployment under the ice. Okay, here comes the autonomy function that I would like to mention a little bit. In the end, it's all about a search strategy. Where should we go? We cannot directly interfere with the system. So the system should have some plan, some search strategy integrated. And that's what autonomy, artificial intelligence is typically doing. Sometimes people say autonomy means autonomous decision-making, and that's what is actually needed here. So first of all, we need what is today often called situational awareness. And this is information that is collected piecewise. It will be built up step by step. And the mission planner, this search strategy, has to be a robust strategy that is not, if you get a signal that is not exactly matching into the picture that you're currently built up, it has to be evaluated. So this is typically some sort of expert knowledge that comes from ocean science that has to be included in that. And there's already some ideas on how to do that. And yeah, I think there will be solutions that can be found, but it's still a lot of work that has to be carried out. There's an active research going on in the US, but in other countries as well. There's a group in Norway who's very active in that. And this picture that you see here is actually taken from one of their publications. All right, so I think, here comes the Earth analog mission that we have in mind. We are not the first that are doing such type of missions. You see here an experiment that has been carried out by Brittany Schmidt from Georgia Tech. And she has been working on so-called ice fin system, which is very similar to what we have in mind. One thing that could make a difference, or probably will make a difference if we are successful, is that our underwater vehicle will have a much smaller size. The one from Brittany Schmidt is of the order of 1.5 meters long and something like 20 meters in diameter. So that caused some issues if you want to go through the ice. But as you can see, this is a very active field and many people are trying to find good solutions that will be useful for space applications as well. So how could a possible Europa mission timeline look like? This would be pretty optimistic to say we can launch it in 2030. It probably will be later. But in any case, we have to take into account it takes about 7 years to go through Europa, and then another 2 years to go through the ice. So that's just roughly something to keep in mind. So it's not like Mars, where you say you start a mission and then a few months later you can start your exploration phase. This is completely different, and that makes all this planning process so difficult. Yeah, what we are hoping for, I already mentioned this, that we can piggyback on a NASA mission. That would be fantastic if this could work out. So we have to adjust our time schedule a little bit with what is going on with NASA. Not sure whether other space institutes has similar ideas, and even, you know, the private sector, sometimes looking what SpaceX is planning to do. I think they are more focusing on Mars missions. So for the moment, I think that's the only option for us if we actually want to get serious and have our triple system deployed on Europa. We have to find a way how to cooperate with NASA on that. Okay, and this is here now my final slide, some food for thought. And what you see here is a few bullet points that I think are very important as a summary as well. You see there's some significant technological barriers that we have to overcome. And I mentioned this already. This has to do with the melting process, that has to do with the operation of the underwater vehicle under the ice. And that's something we want to address, and we hopefully can come up with a good solution for that. But it's really a significant technological barrier that we are working on. So what we also have to keep in mind, for the moment, there is no clear idea, no clear concept, what we actually should look for, how we can find biosignature, or how we can detect life on other planets or moons. And so it will be purely exploratory. So the information that we get from geophysical information can actually help us, but in the end, it's still completely open. You can not really predict what's going to happen. I also would like something that actually discussed with Larry before. Shall we assume that life is an inevitable step in planetary development, or is it a purely random process with unknown probability? So you often hear people say, I'm 100% sure, as soon as we get the mission ready for Europa, we will find signs of life, we will find biosignatures on other planets. It's like a necessary step in planetary development. It's probably something that should be looked more more closely. And so people sometimes forget that in all these process steps that leads to life, there are different probabilities that have to be taken into account. And so no one for the moment knows how the probability is that life will develop on another planet and what the crucial step will be. We have no clue at all for the moment. So not sure whether I should be very pessimistic, but optimistic is also something that is probably something that's not very well justified. And the next thing is, even if we find life forms, what does it actually mean? Could it also mean that it comes from Earth, that so to say, there's some exchange of material between the planets of our solar system that could actually mean this life form actually stems from Earth? And the final question, maybe we can start a discussion on that. Is it actually possible with such type of robotic mission to get a final answer on biosignatures, or that we can find life on other planets? Or isn't it better to think about a sample return mission? So all these questions are discussed within expert groups, I'm pretty sure. And I just wanted to mention it here at the end because I think it's important to have a good picture of how we should categorize the activities that we are doing here within Triple. So that's all I wanted to present, and thank you very much for listening, and I'm happy to take any questions.
Well, thank you, Christoph. We have time for Q&A. I think you can stop sharing your screen at this point.
Okay, yeah.
Zoom participants can raise their Zoom hand or type their question in the Q&A panel. You raise your Zoom hand, I'll call on you and unmute you, and you can unmute your mic and ask your question. YouTube viewers can also ask questions using the YouTube chat box. Those text questions and the ones that are submitted in the Zoom Q&A panel will be read out loud so everybody can hear them, and you'll get an answer. So let's start with Colin Alberts, a PSW member. Colin, if you'll unmute yourself, you can ask your question.
Dr. Waldmann, I wanted to ask you if you could build a little bit more on the communication system that you have in mind, because I wanted to know theoretically, how would a European underwater probe really effectively communicate with an orbiter of Jupiter when it could only do, even if it were doing periodic flybys of Europa? Because even on Earth, an underwater vehicle is restricted to extremely low frequency acoustic waves with frequencies that are so low that communication speed is only about a kilobit per second. And that's to a receiver that's relatively nearby and always there. You were talking in your lecture about communication frequencies of up to 100 megahertz. And I'm wondering, how is that going to be possible underwater in the European environment? And then, you know, if the submarine probe can't surface through the ice, it seems difficult to get any. How would you get usable amounts of data if the transmission is only going to be about a kilobit per second back to the spacecraft bus, let alone get that data back to Earth?
Right. Thank you very much, Colin. Yeah, I was a little bit, there was some misunderstanding that I produced. So definitely you're right. You cannot transfer signals with 100 megahertz frequency underwater. So typically you, depending on the range, you operate between 10 kilohertz and say a few hundred kilohertz. So that's what you can make use of. And yes, you're also right. The data transmission rate is in the kilobaud range, but typically you could expect something of the order, say a few hundred kilobytes per day to transfer. So that's what I would predict. Still, there's some uncertainty, but you also mentioned that you cannot permanently transfer, but that's just a number that I wanted to so throw into the air. The other thing that you were asking for is the communication through the ice. So there's also the idea to use acoustic transmission system, but you can probably also use RF. But the thing is with RF, it also depends a little bit on the ice structure or whether you have some material, some sediment in there and so on. So different factors influencing that. I think that was the reason why people are thinking about this PAC, this relay station, to deploy in the ice to ensure that there is a more reliable connection using RF communication. But in the end, I think that's what you're aiming for is you cannot expect to transfer video images through this communication link. And it's probably just health status and some basic environmental data that you can transfer. Does this answer your question, or?
It does mostly. I mean, I'm not a total expert in underwater engineering and underwater communications, but it seems to me that the Navy communicates with submarines on Earth at a frequency of 3 to 30 hertz, not kilohertz, just hertz.
Okay.
And so I mean, and that extremely low frequency is what really limits the data rate transfer. And I'm just wondering, you know, it just seems an interesting engineering problem to accomplish on Earth, let alone on a moon of Jupiter.
Right. No, I think, Colin, what you're mentioning is this long-range RF communication that the Navy is using to talk to their nuclear submarines all over the world. And that's actually just a few hertz that they are using. You're absolutely right. But what we are doing here is we want to use an underwater acoustic communication system that has a very limited range. Just depending on the frequency, something between a few kilometers down to just 100 meters.
Oh, okay.
So that's completely different to what the US Navy is doing with their nuclear submarines, where they say we want to reach them wherever they are on the world oceans or in the world oceans. So.
Okay, thank you very much.
Mm-hmm.
I suppose as a follow-up question, if you considered using some kind of a light laser kind of arrangement that would communicate to where the probe came through underneath the ice, would have a receiver that could detect the signal from the nano AUV, that would be a light-based signal.
Yes. Yes, definitely. That would be an option. And that's something that we would consider as well. But in the end, for the moment, we are focusing on this acoustic communication because we think this is more reliable. There's an issue with optic communication. It's very sensitive to turbidity in the water. And if you go at larger distances, the data rate goes down quite a bit. The main advantage of optical communication underwater is really the low delay, the low latency. You have faster propagation times. You can immediately send signals back and forth. But
also the bandwidth.
The bandwidth is it's limited, and that's because there is a lot of the signal to noise ratio can go quite up as soon as you have some turbidity in the water, and that's an issue.
And tethering,
excuse me.
I guess tethering would be too weight sensitive.
Tethering is something
there.
that's currently considered by NASA. And you might have seen the small two-wheel vehicle that was on one of the slides. This actually is an idea of NASA. It will be a tethered system. And they say they don't trust these acoustic communication systems, or not the optical systems. And therefore, they are operating with the tether system. So something that we will explore in more detail. Maybe we can come up with an idea of how to go ahead.
We have a couple of questions from PSW member Frederica de Rima. Frederica?
Yes, thank you. Thank you for your very nice presentation. Actually, I had two questions. I'll ask my second one, which is related to the discussion we have. We don't know, I mean, there may be turbulence, there may be kind of a very fast currents. I don't think this has been quantified. So in that respect, and in the context of what you said, that, the communications will be short range, how can you guarantee that? Because, your nano UAV or AUV may be kind of be drifting quite a bit. So how do we, have this been addressed? And there are other related issues that, what is the constitution? I mean, we don't know the salinity there may be very corrosive and things like that. So how,
yes. Very good. Yes, very good. So these are very good questions, Frederica. Thank you very much. So first of all, if I come back to what you just said with the salinity and so on, so you have to adjust the weight of the vehicle. And that's something that we will include. It's so-called buoyancy engine that we will have in there. And to be sure that this is adjusted properly, we can take measurements before of the salinity and temperature before we deploy the system, and then adjust the buoyancy accordingly. So that's something that we have on our agenda. As soon as we break through the ice with our melting probe, we are able to take these measurements and then adjust the weight of our underwater vehicle. The other question that you had were about the currents. Again, this is something that we have to measure before we deploy our system. And I assume that for now, I would say the current should not be stronger than 1 meter per second. If it is the case, we have an issue. We cannot deploy it. So we have to make sure that it stays below that limit. And yeah, that's again something that has to be measured before we deploy it. So from the melting probe. Does it answer your question or?
Yes, thank you very much.
Okay.
Do you think any of the synthetic aperture radars or other instrumentation being sent to Europa prior to the triple project will be able to tell you anything about currents, movement of water under the ice? It just can't penetrate that far.
I don't think so. So no details. I don't think that we get all the details. But you know, the ice penetration radar would help a lot to clarify the structure of the ice, whether there's some material, some sediment in there, or even rocks or something like that. So I think that's the primary purpose of using this ice penetrating radar, as far as I understand.
Have any of these missions considered putting seismic or some kind of a sensor on the surface that might be able to give you some information about the movement of the water underneath the shell?
That's will be the case. Sorry, I just deleted this, but it will be part for the lander mission. I didn't want to make such a long list, but you know that is actually on the plan for the lander mission of JPL, seismometer. And as I mentioned before, you know, passive acoustic is also a fantastic tool to be used and then to classify processes that might occur. Mm-hmm.
We have a question from PSW member and GC member Connor Nixon, who works out at Goddard, and he asks, what would be the duration of the AUV? And how long will it last? And a follow-up question to the discussion of communication, he also asks, how is the data going to be returned to Earth?
Right. Okay, so the duration, it's something we calculated something of 2 to 3 hours per mission, so to say. What I just mentioned briefly is we will send out the AUV, it will come back after 2 hours, and then it should dock to the melting probe and then be recharged. So it's we will not have more energy available than just for 2 or 3 hours. And this is a scaling problem. You know, if you go to very tiny little underwater vehicles, you're very energy limited. And so, you know, if you translate it to a range, it's about a few kilometers that you can reach, so to say, as a range for the vehicle. And then there was a question about the communication.
Yes, how is the communication back to Earth going to
Back to Earth. So there's this deep space network of NASA that could be used. And so as far as I understand, for the lander mission of JPL, they want to have an orbiter so moving around Europa, and then this is used as a relay station, and there will be a RF transmitter on the lander system. And it's something similar that we would have in mind. So for us, our lander is the Astro Biolab that I showed on one of these slides, where we could put a RF transmitter on.
So it's basically from the nano AUV to the probe that has gone through the ice and is now underneath, up through a wire to the lander, from the lander up to the orbiting satellite, right, and then back to Earth from the satellite.
Right. Yes, correct. Yeah, I think.
So let me ask Mayumi Okada, another PSW member. Mayumi, do you want to ask your question using your voice, or should I read it? Okay, I'll read it. She wants to know if there's a chance there's an air pocket between the ice and the water, and whether or not you think there is one.
On Europa, I would say no, but you know, there's just this tenuous atmosphere, and so for the moment, I cannot foresee that such pocket could exist. What it could probably is possible is that there is a fluid pocket in the ice. That's something that we also see in Antarctica, but not filled with gas. I would not expect that.
We have a question from Joel Wilson, another PSW member and a physicist. Joel?
Yes, Doctor, thank you for your presentation. A question. I noticed that you mentioned that Europa had a high radiative signature. When I remember reading early on when we were going through the Galilean satellites that it's being modeled as going inside of a plasma tube around Jupiter. Is that the source of the radiation?
Exactly, yes. So to say, the Jupiter is collecting the solar wind, the particles, and this is causing this plasma ring around Jupiter. And I think that's Europa is one of the places in our solar system with the highest radiation exposure. And so that's all because of Jupiter. You're absolutely right, Joel.
Okay, thank you, sir.
We have a question from Ivan Becky, another PSW member. Ivan?
Yes, Dr. Waldmann, my question concerns the energy required to penetrate the ice and how long it takes. You mentioned that a 2-year time will be required to melt your way down through the ice. It sounds to me like you must have an energy source that can't generate very much heat if it takes 2 years to go through. So my question really is, what about using an RTG, a radioisotope thermal generator, to generate the heat to tunnel down through the ice, similar to the power sources we use for planetary probes? Have you looked at going down through the ice much faster using an RTG?
Yes. So what I mentioned, the RTG was not explicitly connected to the ice melting probe, but actually this is right. There is a plan to put an RTG into the ice melting probe and then use the produced heat to melt through the ice. That's exactly a concept that people are also pursuing.
How long would it take to tunnel? How long would it take to tunnel through the ice using an RTG of today's design?
Yeah, sorry that I feel a little bit uncomfortable to make exact statements here, but it's somewhere in the range. I think maybe it's 1 year or just in the range of few months. So, but it will not go within days.
What did you say?
Won't go into. Thank you very much.
Okay, thank you for your question.
We have another question from Carl
Won't
Merrill.
go down in a day.
No.
It takes a lot of energy.
Yeah.
Yeah, definitely.
Did you unmute yourself?
Yeah, I did.
Now you need to mute yourself. Carl, you have a question?
Yeah, yes. If I heard you right, you said that you can't see underwater, but of course with sound you can generate images, and certainly with ultrasound you can generate fairly detailed images, and sound travels over great distances. So I wondered if you'd comment on that. And the other thing is that all of these efforts to look for life on other worlds assume that the life is going to be primitive, but the Europa has been there as long as the Earth has been here, presumably. So we've got fairly complex organisms that live under our ocean, and it seems it would be not too expensive to have some sort of probe to look for signals from some sort of more intelligent entity that might be under the water there.
Yes. Yes, thank you. First, I would like to answer your question in regard to acoustics. Yes, you are right. Acoustic can provide some detailed information, The thing is, we are space limited. We cannot use these big antenna arrays that you probably think of if you have seen these high resolution sonar images. What we will probably have to do is to build up a sonar image piecewise. So we say while moving through the water, we collect additional information. So that's, so to say, the issue that we have with the size of our vehicle that would not allow us to have these high resolution images produced immediately. But yes, definitely, there are systems that can provide high resolution image. You're right, but for us, it's probably not possible because of the space limitation. And then you were asking for higher life forms. So I would like to come back, we had a similar discussion with Larry, to what people are thinking about development of life forms. So I have colleagues at the University of Bremen who say they are 100% sure that we will find on all planets of our solar system biosignatures. So they say there was a phase when the life have developed very similar to Earth, but then it stopped because of different reasons. And some of the reasons are probably the impact of meteorites or something like that. So there, in some cases, there have been some fatal issues in the planetary development. And so what about Europa? For the moment, we cannot really say what has, let's say, happened in between. We just, many people are thinking the ocean has been in existence for the same time as on Earth, but still this is then the question, do we have enough organic material there? Is there all the prerequisites available to develop higher life forms? Or how can we actually judge on that? As for the moment, I would be very careful on that. I know people are very optimistic that they can find fish there, and then we don't need any sophisticated sensors. But for the moment, I still have my doubts. We don't know enough to make such a prediction. But yes, we will be open to any ideas in regard to also look for that. And therefore, people will always say we need a video camera. So we not just want to have sensor systems that delivers measuring values, but we want to see what's going on there.
Well, the last thing I'd like to mention is that almost all of our deep sea exploration here on the Earth is done with craft that are tethered. They're not free swimming. So they have fiber optic cables, so they can transmit data at very high rates. But when you presented it, and in the discussion, people seem to be limited as to how much data could be transmitted. So I don't understand why. Surely you're thinking about tethered craft that can transmit back, and of course, then you could have computers on the surface that could do anything you needed.
Okay, you're right. So we have been thinking about this, but in the end, we want to make a step ahead, and there are many people thinking about having an autonomous mission carried out by underwater vehicles. And you're absolutely correct. All the major findings had been carried out with tethered vehicles, and video cameras play a big role in that. And so it's not the plan that we want to replace that. We want to learn from these missions. So what people have learned from that is how to design an exploration strategy. And that's exactly what we want to integrate in our AOV system. So we cannot, so to say, go beyond what people are doing today with tethered system. We can just say, maybe can, to a certain extent, do something similar. So that's the idea. So that's what I wanted to indicate with this expert knowledge that will be integrated into the AOV system. But still, it's lot of work to do. You're absolutely right. This is not a very easy task.
Well, of course, there's a penalty to tethers, which is the weight. So if you want to have a very long tether,
Right.
it's going to weigh a certain amount, and the spooling mechanism is going to weigh a certain amount. You have to get it all the way there, and then you have to get it under the ice. So there's some penalty
That's correct.
associated with that. But yeah. So we have a question from Mike Helton. Mike, if you would like to ask your question.
Yes, thank you, Larry, and thank you, Christoph. Very good presentation and answers a lot of details about that kind of mission. I was thinking that if Europa has any geysers that shoot off some water from the subsurface, it might be a consideration to have an orbiter around Europa to go through those geysers and pick up some samples of possibly some biosignatures of the particles coming out from the subsurface water.
Exactly. Yeah, this is exactly a strategy that NASA will also follow, in particular in regard to Enceladus. So they will definitely not consider a lander mission for Enceladus right now, because what you just said, people would expect that you can extract most of the information that you can get from a landing mission also from an orbiter. And so it's not 100% clear to what extent this will work for Europa, but for Enceladus, people will exactly follow the scheme that you just suggested. So just stay with orbiter missions, no landing mission. So it's still unknown. We will hope that we can get more detailed information on these plumes from the Clipper and Juice missions, but yes, one has to.
Okay, thank you. Thank you.
It's definitely right.
Dick Garwin asks, what is the temperature versus depth relationship expected to be in the Europa Ocean? What do you expect the temperature versus depth profile to look like for the ocean?
If I would say it's similar to the Arctic or Antarctic, then it will probably just vary by a few degrees centigrade. So if you look at the temperature profile in the Arctic Ocean, it varies by 1 degree or 1.5 degree, going from the surface down to the bottom. And this is, by the way, have you heard about this deep convection, where you have exchange of deep water with surface water? This is just possible there where you don't have this layering. And this is where, for Arctic, a very typical phenomenon.
I think it's kind of a fascinating thing that the temperature of the water on Europa is likely to be very similar to the temperature of the water in the Antarctic and on Earth, just because of the properties of liquid water.
Right.
It's a question from YouTube. Eric Enig asks, is there any expectation that Europa may contain skylights from historical meteorite impacts, not dissimilar to those present above lunar lava tubes? And I'm sorry, Eric, I should have asked you if you wanted to ask the question yourself. So, oh, I'm sorry. No, you're coming in from YouTube. Sorry, forget it. Let me ask it again. He says, is there any expectation that Europa may contain skylights from historical meteorite impacts, not dissimilar to those present across lunar lava tubes?
Yes, one probably can expect that, but the surprising thing is that on the pictures that had been taken from Europa, there are no big impact craters. So seems that this is not too much, has been not affected by meteorites too much. But in any case, you cannot exclude that there will be meteorites in the ice or in the oceans.
So next to the last question, Robert asks, 10 to the 5th meters of ice. Would a crawler or climber from a space elevator project work? I'll let you answer that one.
Not sure whether I'm too familiar with the space elevator system, but maybe someone else can respond to that or give me a hint.
I think you said it was about 10 kilometers, so I think he's off by an order of magnitude.
Right.
That would be 10 to the 4th meters.
So I'm not sure what is meant with space elevator.
I'm not exactly sure either.
All right, okay.
I think the last question is a more general one, not specifically related to this project, but between the German Space Agency and NASA. And the question had to do with what really is the relationship between the two? Does German Space Agency compete for NASA money to do projects? Are you ever the lead agency on a project, or are they more, you may design a project, or you may make an instrument or participate in some way on a NASA probe, or is it a fully cooperative kind of development?
I think all of that.
All of them, okay.
And so
That's
our
good.
plan.
You work together any way you can.
Yes, right. But our plan would be to partner with NASA and then so take full responsibility for a subcomponent of a mission. So that would be our vision for a cooperation. And yeah, but for now, I must say, we are still in some sort of brainstorming concept phase. And so we're exchanging ideas, and we haven't made concrete plan on how to go ahead. But, you know, in the past, there had been different templates on how this cooperation could go. And it was also that each space agency gave their money into a project. And then I think there was a telescope which was integrated into an airplane. So where
Sophia.
Cost had been shared. There was some cost.
Sophia, it's a joint project.
Right.
NASA paid for the plane, but I think the optics and the carriage that isolate the telescope from the vibrations is designed by the Germans,
right,
by you guys. So I guess my follow-up question would be, are you working with Are you working with JAXA? Do you work with the Indian Space Research Organization? Is there anything going on in that direction with other countries besides NASA?
Not in the context
Australian?
of Europa. Not in the context of Europa. There had been cooperation with JAXA before. There was this mascot project where Germany has cooperated with JAXA, but for now I have no idea whether there's an interest of JAXA in Europa.
And I guess the last question is, for launching the Triple project, are you required to use Arianespace, or can you use anything from Russian launch vehicles to SpaceX to
Yes.
ULA or whatever is most economically sensible?
No, we are not limited to Ariane. We can use other space systems as well. And you probably know that Germany is often using the Russian capabilities.
Yes.
Because it's cheaper and yeah.
Very
Ariane
reliable
is
too.
more, yeah.
By far, actually, the most used space launch system.
Right.
So, all right, I think we'll wrap up there. I want to thank you, Christoph, for giving a very informative lecture. I think for us, it's very exciting to have an early view of this very complex and ambitious project, and part of an effort internationally to go to Europa and look for life there. And we look forward to hearing talks on some other aspects that you touched on tonight of other missions that will integrate with the Triple mission, and to hearing from you again as things progress. And it looks like we're at a point where it'd be a good idea for you to come in and tell us where things actually got to. So really, it's been brilliant having you, and really appreciate your staying up this late for us and sharing all this information. So it's been great. Thank you so much.
Thank you very much again for the invitation. I'm very much appreciated being here.
Our honor and pleasure to have you.
All right. Thank you. And bye-bye.
Bye-bye. So the recording of tonight's lecture will be available to everybody on the PSW YouTube channel and in due course on the PSW Vimeo channel and via the PSW Science website. Please share the link with your friends and subscribe to the channel for notifications on new postings. But before you go, we have a few announcements. The 2431st meeting and the next lecture will be in 2 weeks on Friday, December 18th, 2020, capping the fall 2020 lecture series. The speaker will be Kang Kwan Ni. Her lecture will be on amazing and interesting experiments that visualize quantum states and processes and enable the atom-by-atom assembly of molecules under the control of the experimentalist. The spring schedule is being put together and will be posted to the website in the coming weeks. Check there often for updates. And before we go, last but not least, please join me in thanking tonight's crew for producing tonight's event. James, Ann, and Robin, our heartfelt thanks to you. And I will now adjourn the 2430th meeting of the Society. I wish everyone a good evening, and I wish you could all be joining us for the social hour together, but since you can't, please enjoy your social hour at home. The meeting is now adjourned.